Sure. That's not great. What happened to that? It was there at the end of August. I don't. Now, just making sure there's nothing accidentally profane in the slides. But now it's disappeared completely. You go for that. But now I don't know where the slide is. Well, no, I should disconnect, but no, it's over there. Like in my bottom's gone too, so it thinks there's another monitor somewhere. But that's because it's doing that. There's another monitor somewhere because that's where the presentation is. I dragged it over there. Well, I can't do that until I can see it. Well, now I can play it. That was me. I don't really know what those words mean. What? No, no. I like it when it shows you what the next slide is. Okay. Great. If it's green, it should be off. You could do it. Testing. Ooh. Ugh.
I heard the tapping.
Oh, you're on.
Okay. Hello, welcome everyone to our first astronomy night of the year. We're very excited to have you, and we're excited to hopefully have a full year of these talks. I know we haven't been able to for a while, but we are excited to be back. This week we had a special astronomical day. On Monday, it was the fall equinox. That means that there was equal amounts of light and dark that day, marking the start of fall, so equal equinox. From now on, every day will have a little bit more darkness than light until the winter solstice, where we'll have the most amount of darkness in the day. The equinox was a very important time of the year for cultures throughout the history of the world. So humans all over the world have been observing Earth's place in the solar system, charting different phenomenon, and then putting holidays and cultural practices around the astronomy phenomenon. All right, but today we're not going to talk anymore about the equinox. We have an exciting, if I turn the clicker on, an exciting day for you. We're going to start, as always, with trivia. We'll go through some announcements, and then we'll hear from our speaker, Dr. Nick Luber. Then we'll have raffle, and then hopefully we'll observe the weather is looking a little bit dicey. If we don't have clear skies, I'll do a simulated tour of the sky tonight. So no matter what, we'll try to look at something. Okay, trivia. How this is going to work is I will show you a question. I'll give you some time to think about it. Collaboration is deeply encouraged, so talk to folks around you, especially if you don't know someone. Share your collective knowledge. And then after some time, I'll ask you to vote, and you'll give me 1 for A, 2 for B, 3 for C, 4 for D, 5 for E, and then we'll reveal the answer. Your first question. How far can radio waves travel in 1 second? Is it across Central Park, across New York State, across the continental US, one around the Earth, or to the moon? So I'll give you some time to think.
This wasn't a work with people, but
He's coming. Collaboration is encouraged. Okay, 3, 2, 1, vote. Let's see answers. Okay, I see a lot for E, some for D, some for B. All right, I don't think I see any for A or B. Nick is saying E, so hopefully for his credibility, that is the right answer. And it is. So remember, it took humans 3 days to travel from Earth in a spaceship to the moon. And that was going very fast. So 3 days compared to 1 second should give you some context for how fast light is. All right, question number 2. Which of these have a longer wavelength than radio? So radio is a kind of light. The kind of light is dependent on its wavelength. It can be big or smaller. So which kind of light has a longer wavelength than radio?
wait.
Okay, let's vote. 3, 2, 1, vote. I'm seeing some ones, I'm seeing some twos, I'm seeing some 5. All right, let's see what the answer is. It's 5. So radio have the longest wavelength of all kinds. Question 3. Which of these uses radio waves? Cellular communication, radar detection, TV broadcasting, barcode scanners, remote controls. All right. That's confidence with this one. 3, 2, 1. All right, I see some ones, I see twos, I see 3s. I see 5s. I don't know if I see a 4. All right, well, this one we were cheating because it's multiple. So I think collectively I said I didn't see any D's. So I think we all collectively as a room were correct with this. So we can use this kind of light that we can't see with our eyes to communicate with other kinds of devices. So radio waves are very useful and important for human technology, not for barcode scanners. I think those use lasers. All right, question number 4. Who was the first to detect radio waves from space?
The yellow, right? Bell. To become yellow. I met her. she gave me double.
Okay, 3, 2, 1, votes. I'm seeing 3s, 4s, 1. All right. And this one, it was just one person this time. And it was Carl Guski. And so a common unit that you'll see around this field is the Jansky, so named after Carl. I remember from my days of a student that it is a confusing unit. So I will let Dr. Luber explain it and not me. Okay, question 5. How big is the biggest radio telescope dish in the world? Your hint is it's called the 500-meter aperture spherical telescope, and it is in China. I frequently torture my students with these kinds of questions. Unit conversion, we love it. All right, 3, 2, 1, votes. All right, I'm seeing some 2s, 4s, 5s, a 1. I don't think I see any 3s. And the answer is 135 Times Square New Year's Eve ball. It really makes you wonder about people who run marathons, right? That's too far to run. All right, usually we just have 5 questions, but today we have a special 6th one. Yes, very, very exciting day. This question is very special and is something that our speaker is passionate about. And it is, can you listen to radio waves as they showed Jodie Foster doing in Contact? Okay, 3, 2, 1, votes. Oh, I'm seeing a mix, Nick. No! You cannot listen to radio waves. The device radio was named because it uses radio waves to get signals. Those are light signals that it then converts into sound, which our ears can hear. So sci-fi does not always help out astronomers in trying to convey correct information, but that doesn't mean we don't have to enjoy the movie. All right, thank you all for playing trivia. It's always fun to check in our prior knowledge. And hopefully we'll add to that knowledge that you have. Quick announcements. If you are not on our mailing list already, this is the best way to find out about our events. You can go to our website or you can email me. But this again is the best way you can find out about events that we're having. We do have a talk lined up for each month. This is the schedule and our speakers. So there'll be announcements 2 weeks before each talk. And the fall typically is the best luck we have with weather for observing. Tonight, not so sure, but hopefully this fall we'll be able to do lots of observing. And with that, I'm going to hand it over to Dr. Nick Luber, who will give his talk, What If Our Eyes Could See Radio Waves?
Thank you. Hello. Is the mic on? I know you all can hear me. Okay, but the mic's on, just because for the people online. I regularly teach in this room, so I know you can hear me. But extra trivia. Why is this picture deeply wrong? Your eyes see color.
Showing visible light.
Let's say that as a person, I saw this into the sky, so I would see the beautiful pictures of the telescope and the night sky. Why is this deeply wrong? No, that's fine. We're just looking. We're sitting, laying on the ground, looking at the Very Large Array, which is the name of this telescope, and looking up at the night sky. What? The sun could be setting, which is fine. Yeah, this is kind of silly. I don't think anybody but me would really care. But you wouldn't be able to see this. So this is a fake picture. You can't see the you can't see the small Magellanic Cloud from the northern hemisphere. So whoever made this picture is a liar. Yeah. But that's just a fun little thing. Okay, so hi everybody. I'm Dr. Nick Luber. I am a lecturer in the Department of Astronomy here at Columbia. Somewhat whimsically, I went to Columbia for my undergraduate degree, as did Amanda. Oh, fun. And I took intro physics in this class. And where do you think I sat? No, I'm not a nerd. I sat actually right in where the gentleman in the red shirt is. I sat there for every lecture that I came to in this classroom. So kind of funny. But so I like to start every lecture off with this silly Oscar Wilde quote, which is we're all in the gutter and some of us are just looking at the stars. And I really hope to underscore this part of astronomy that I think is sometimes lost on people. In this day of age, as everyone talks about big data and understanding the universe. And I say, screw all that. Let's just look at the sky and see something really cool. So I hope that's what this talk gives you at the end, is that desire to look at the sky and see something really cool. There are kids in here, right? Yeah, okay. Because I would have put an expletive in there, but I will not for the sake of the youth. Okay, so today's question that we're specifically going to ask is what if our eyes saw radio waves? A look into an ultra deep image of the radio sky and the physical mechanisms at work. So the first part is the fun tagline. The second part is the actual science we're going to get to in addressing that fun tagline. All right, so I have a couple of current students in here right now. They've only taken 3 classes with me, so they can probably attest, but maybe not full-heartedly, is that I value audience participation. So you all are going to, again, there we go. But will you have prizes? Yes. So, when we look up at the night sky, what do we say? Stars. Great. Wait. What else? Planets. Great. What else? Satellites. Great. We don't like satellites, but we do see them. Yes. Galaxies. Awesome. Oh, that was a great throw. What else? Nebulas. Awesome. We have a budding astronomer back there. Oh, another great throw. Yeah. The moon. Everybody's favorite satellite. What else? Comets. Awesome. We definitely see comets. What else? Starlinks? Someone said satellites, but I'll take it. Oh, that was a terrible throw. Yeah. UFO? So we won't mention those again in that class, but I'll give you candy for it. Yeah. Again, we said satellites, but I love specificity. What else? So we see galaxies. We do see specifically our galaxy. Meteors. Yeah. What? We see clouds. How terribly depressing. Planets. We already said planets, but I love the enthusiasm. Way in the back. What? Shh. Planes and helicopters, definitely here in New York City. We see planes and helicopters. Yeah. We could. Not here, but we could. All right, I think we got all of them. So, long story short, when we look up at the night sky, we see a lot. We see a lot. So let's talk a little bit in more specificity about some of the things that we see. Some things we see from the night sky are from our solar system. So we see the moon, everyone's favorite satellite. We see it in different phases, and it cycles through those phases. We see planets. What do I say? Yes. Planets at different times as we all make our way around the sun. Different planets are apparent at different times of the year based off of their orbits. We also see the occasional comet, asteroid, and or other space debris. Oh, excuse me. And with that, I include all satellites and other man-made stuff because those are boring. Oh, and here's a pretty picture. So in New York City, where we all are, of course, we can see the moon. We can see Venus, which is the brightest object in the sky when it's up. And how many stars do we think we can see here in the city of New York? Not enough, definitely true. Any guess? What? Oh, wow. That's terribly correct. We can see 15 to 16 stars in the New York City sky. All right. So moving on, we see stars from all over the place. Specifically, we see them all over the Milky Way galaxies. And stars are bright, point-like objects that come in a variety of colors, sizes, brightnesses, magnitudes, and they are more or less, for at least our eyes, uniformly distributed along the sky. You can see here exactly what I said. We have different colors. We have some brilliant baby blues. We have some nice dark reds. We have, I don't know, that looks yellow to me. And everything in between. We have all kinds of sizes, shapes, and those correspond physically to all different types of stars, which we will not talk about again because I don't like stars. And then we also see the beginnings and end of stars. So someone said nebulae. So in here we'll see this. So here we have my favorite constellation, Orion. And right here where Orion's sword would be is the Orion Nebula. And the Orion Nebula, we have one graduate student. I don't know if there's any other graduate students who could correct me. But I think the Orion Nebula is a reflection nebula because of a recent burst of star formation. Graduate student? All right, good, because you're the only one who would have corrected me. So that was a laugh line. All right, so we see these big, diffuse, beautiful structures, though, and they often indicate the beginnings of stars and the end of the beginning, because stars form in these things called molecular clouds, which are full of gas and dust, and the young stars, they sort of reflect light in funny, beautiful ways. And at the end of a star's lifetime, when they explode, you get beautiful pictures too. And one you can think of that most of us could actually picture is the Crab Nebula. So the Crab Nebula is the end lifetime of a star. Cool. And then we have galaxies. So like we saw in the beginning, we have the small and large Magellanic Clouds, which are our nearest galaxy counterparts, right?
Yes.
I think so.
Yeah.
Yeah, I think so. In any case, and they're pretty big. They're less than 10% the size. So they're low mass counterparts, but they're very near, so they appear very brilliant in the sky. And to get a good view, you really have to go to the southern hemisphere. And then last but not least, we see our own galaxy. This should be shocking because I am saying that this is our galaxy. Why does that shock and appall you? Yeah. How the hell did we get the picture of it? I know, right? That's a great question. It's because we're actually not seeing the entire Milky Way galaxy. That was worth a candy. You said it with such a glassy-eyed enthusiasm, too. Is that we're not getting a picture of the entire Milky Way galaxy. Instead, this picture is us here on Earth looking towards the center of the Milky Way galaxy. So there is more to it beyond what we see in this picture. But from here on Earth, this is our impression of the Milky Way galaxy. So if you ever see a picture and it shows the Milky Way galaxy, it has beautiful spiral arms, it has these beautiful dark red and deep bright blue nebula, it has these lanes of brown and black dust. Is that a picture? 3, 1, 2, 3? No, because we've never been outside of our galaxy. From outside of our galaxy. So when you see that image, it is an artist's rendering. It's really important to think about that in astronomy because more often than not, artists' renderings are the interesting things. But we need to ground ourselves and remember that they're just that. Cool. All right. So what can radio waves tell us about the universe? So now we're going to do some everybody's favorite 7-letter P word. Physics. There we go. So we're going to do some physics. We're going to talk about what actually produces radio waves. But before we can do that, we need to say, what are radio waves? And what they are is a part electromagnetic spectrum, long wavelengths and high, or sorry, long wave, you get B, A, radio. Then astronomy. Anyone know what it's a chocolate bar, and for that, you get a chocolate bar. So some nice gentleman in the lab somewhere in the Arm of America, which is Jersey, not New York. So no big deal. Hello, buddy. But no, so the first place was I think at Bell Labs in North Jersey, and they were experimenting and their firm. But at the end, he was like, "Oh, he found out that actually electromagnetic waves are that paper, like so in a case then we have infrared, with our night vision goggles, whatever the hell else could we use infrared wave for? Visible, like we said, ultraviolet, which we all hate. Cancer, those high energetic waves. But that we have X-rays while you're control. Why do we all care so much about X-rays here in this? All right, I'll become a current Columbia student in my class. What's the name of this building? What's the name of the building? So Michael Jaworski Pupin was the first ever X-ray. So that's also really cool. It's something that Columbia says, but it's really really lucky if teachers the first medicine diagnostic. It didn't go up shop. And from that we found out we can X-rays for medical diagnostics. Then we have infrared, which of course turn people into. Alright, so all of these though are the same phenomenon, just at different wavelengths. Are you all on board? Yes or no on 3? 1, 2, 3. Good. I have no idea what the next slide is. But I hope it's this one. So, can we hear? Hey. No! Because they are just light waves at a longer. Make sense? Make sense? Yeah. People in the cheap seats. Yeah. Good. Back right. So, what do I say relate to that? Yeah, is we tend as people living our lives here on this lovely dot, to put emphasis on optical waves. Our eyes. Good, yeah, it definitely is because the cones drawn in our eyes are sensitive to that. Why? Yeah, it's things that we can read appropriate that way. That is 100% false. They will emit mostly infrared.
Guessing it has to do with enough of them pass through the atmosphere and bounce off of objects that are around us.
That is 100% true. Hold on. So, where is the mother of all light for us here on Earth? The sun has 4 emissions. Optical light than any other. Thus, we evolved to primarily be optical wave. What else do we know about Earth? Blue, green. What's green? Plants. Why are plants green? Chlorophyll. Chlorophyll is what to green light? Good. Some people get that wrong. Color comes from reflection. So chlorophyll reflects green light because most of the light from the sun is green. And in fact, photosynthesis, like a really bad thought, is energetically unfavorable. It is really easy to mess up. So because of that, plants reflect most of the green light as not overload the capability. But most stars, universe, are actually not light. Most of them are no red light. So grass on those planets would be red. They follow the same biological process. That's here. So if you ever see a cute poster from NASA, so that's like yeah, I'm sitting here. So NASA made this really cute poster that says the graph is redder. That's an illusion of that most people probably have red. All right, back to radio waves. Now that we've all learned all about light, what causes radio waves? So radio waves. Oh no, we have. Oh, there's. The other thing I will say about all these different waves, like radio waves, they're all terribly useful in understanding the universe. And the proxy I want to use for understanding the universe is understanding the Milky Way galaxy. You may look at the Milky Way galaxy with every different light at our disposal. So we're going to talk about these first 4 in this lecture. Those are radio waves. But here, these 3, you see what the galaxy looks like in infrared light. Here, galaxy optical light, X-ray, here in gamma. And the galaxy, all these pictures looks because of all of the wavelengths, all of stuff is different. But now we're going to what is manufactured? In order to get to that, we talk about where radio light comes. The most common source of radio, the second most common source of radio light in the universe is by this thing called free emission. And free emission is basically you have some proton. Do you think the universe is full of protons? Yes, you're going to want 3. 1, 2, 3. Yeah. You think the universe is full of electrons? Yeah. Sometimes they collide. So they actually collide very rarely. Fascinating question. What instead happens is they get their trajectory for by one another. Specifically, the electrons get their trajectory by the proton. And when that happens, they emit light at radio. And if enough of those orbits happen, you get a whole bunch of radio waves. Sorry. Next, it's synchrotron radiation. So, this is related, but now, instead, we have an electron. He is free. A free electron. Who electron do you belong to on Earth? Atoms. Who electron do But these electrons are free, and they're actually moving in galaxy-sized ambient magnetic field. Rather than going, they twist around the magnetic field line like this. And when they do that, they release radio. And the way they release them is this equation. We won't pick on our nice gravity. There's another one that we on. Very famous equation in radiative transfer. Yeah, this is a big equation in radiative transfer and high energy. And this is Larimer precession, and it has to do with how to determine how many electrons are based on the field radio waves. So all this is related, and we can use radio waves to find out interesting things about the universe. And specifically, we can ask what happens to this phenomenon would we see in our eyes in radio? We have a couple different things. So first, we see stars. So, yes or no on 3. Would we see stars being born? 1, 2, 3. You silly gooses. My mic. Hello? I don't like that. So we would not see stars actually being formed from radio waves. Instead, what we would see is the death of young stars, and specifically O stars. But young stars die, and they shoot off electrons into the galaxy. And those electrons get tangled in magnetic fields and release synchrotron emission, allowing us to detect the areas where stars were recently formed. Here's just kind of a cool picture of this, is that we can see cosmic ray electrons. Those are those electrons that I talked about that get shot out from those young stars dying. Here is the magnetic field of the galaxy, and here is the radio light. So you see that radio light can be directly back correlated into how many stars were formed. So we say that radio continuum emission can be used to trace star formation. Next, we can see radio emission from active galactic nuclei. More generally, we can see radio emission from black holes. So, what the picture on the outside is a galaxy, a very big galaxy, about 100 billion size of the sun is right there. Pretty, right? Right. Yes, we should always hem and haw at astronomy pictures. And these are actually radio emission. And they're caused by in zooming way in, we actually get but based off that diagram I showed you before, you could also call this microwave. And here we have this plasma ring, which is a glowing magma colored thing around a black hole. And the black hole is that black circle we see. So these are these things called radio transient. So sometimes we see radio. That depends a transient. We see things and then we don't. One example is stacked radio. These are high energetic jets of radio cascading to Earth in under half a from both and distant galaxies. And they hold a special place in my heart because they were discovered by before. Where did it be? jetting across time and frequency. And actually from this curve, tell how far away it was and what was in the way of it here where it came from. The other really important radio transient are pulsars. So here's the schematic of a pulsar. A pulsar is a dead star that is rotating very, very, very quickly. So you can picture here. That sounds very quick. It is very quick. But they get a lot of regularity, and they come with lights at each of their axes, so they look like this. And what does this look like? Thank you. I moved it very quickly. So we often joke cosmic lighthouses because we time them very well as a result of that. And these pulsar timing solutions can be used for everything, finding out what the heck it's actually made of, to the detection of gravitational waves from colliding supermassive black holes 10 billion years ago. So they're a very cool astronomical. So, back. The whole point of this talk is, so what if our eyes saw radio wave? Here is the night sky. Here's the moon. Here are stars. Also very pretty. So now, drum roll. More energy. There we go. Thank you, man. So this is the night sky if our eyes saw radio waves. Super cool, right? So you're all going to drop out of whatever program of study you are or whatever careers you have and go study radio astronomy, right? Yes. So this is what we would see if our eyes saw radio waves. What's really cool, though, is the main thing that we see with our eyes, the optical light, are stars. But every one of these points is actually a galaxy. So if our eyes saw radio waves, it would look, it's pretty similar, right? All things considered, it's pretty similar. But the class of objects we're seeing is wildly different. So we would see all of these galaxies. And let's pick on one. Where is it? Okay, let's go to this guy. Down. What's the next brightest blob? That one. That guy right there. You guys see it? Yeah. That light is shining from when the universe was just 3 billion years old. That's the galaxy, and it's showing us our light. So very cool, very different from the stars that we see in our night sky. But let's talk a little bit more about the funny things in this. Let's do the science stuff. So this is the actual scientific plot that appears in whatever publication. It shows a single field of the radio sky. Do we have any computer freaks? You don't need to look ashamed. Raise your hand. So this is really a feat of computing, at least in astronomy. So the raw data laptops, and that's just the data. And this is 1,000 hours of a telescope. That telescope you saw in the very first picture, looking at just a single part of the sky, and the 512 megahertz of bandwidth. That's not really impressive unless you're in talk, but it's impressive. Thank you. All right, so those are the scientific specs. But looking at some cool, peculiar cases, here are two galaxies. You see here, its brightest point is right here, and then it has these two little arms. Same thing here, brightest point, and then an arm here and an arm here. First off, what do you think these white parts in the image are? First off, this is my public talk, so who do you think made these images? Everybody? Yes, I demand praise. This is my dissertation if you ever want a terribly boring read. This is chapter 3. What do you think the white spots are? Oh, I wish. No. Yeah. The what? The parts that are free from radial light? Is that what you said? Sorry, it's just hard to hear. No, but that's an excellent guess. A black hole, again, an excellent guess. I'll save you all the suffering. It's me doing a bad time at my job. Those white spots shouldn't exist at all. But the data is just incredibly hard to work with, and sometimes you don't get it perfect. And those are residual imaging artifacts. And most of my thesis was spent trying to get rid of them. But this is a cool case where I could not have a bitter failure. No, you're not. Thank you. You get an A. So, what causes these galaxies to look really funny, though, is super cool. So this galaxy here is a active black nuclei. That picture we saw before with the beautiful red lobes and the bright yellow center. This is that, but moving through what's called an intercluster medium. So this is a galaxy in a cluster of galaxies, and what's happening is the cluster medium is bending those arms as it travels through it. Yeah. This one is actually also super cool. It's again an active black nuclei that has lobes, but the galaxy is twisting like this. So the lobes are twisting, but right in opposite directions because they're on opposite ends of the galaxy. And this is super cool because these can tell us a lot about the medium through which those galaxies are flying. So that's the scientific case you could get with those, is you can learn about the environments in which galaxies live. You can also do some statistical studies. Very fascinatingly, this graph shows you the star formation rate, more or less, of galaxies as a function of age of the universe. So this is, oh, no, as the opposite of age of the universe. So this is the universe's beginning, and this is right now. And this is us now, we used to form a bunch more stars, and then we used to form less. So we started off forming a couple, made more and more and more, we peaked, and then started making less. And one of the ways we can study this is by looking at faint radio waves. And this plot here from the paper of mine that I showed previously shows us exploring down here. So this axis here has to do with how bright something is. The further you are to this side, the brighter you are. And you can see there's all these papers that talk about the things up there. Old news. We've been doing that since the 80s. Who cares? Yeah, thank you. That's exactly the reaction I wanted. So now, using the sort of work that I've been doing, we can probe all the way down here and see what those faint sources are doing. And right now, we're beginning to learn more about the properties of galaxies around here. And we can maybe find out why it is they had an increase in star formation rate, a plateauing in star formation rate, and then a subsequent decrease. Was this all super easy and fun? Yes or no on 3? 1, 2, 3. No, you fools. I sat in West Virginia in Morgantown. Any Morgantown? No, it's a miserable place. Although I had a lovely 3-bedroom apartment for, New York. New York adults. Are you ready for this? Are you ready? A 3-bedroom apartment. All to myself. 1,500 square feet. $650. So I'll give it that. The real estate was great. So in my little Morgantown apartment, I spent years of my life whittling away at this question. So all of this work is in chapter 3 of my thesis. And it turns out that when you try to do a deep imaging project like this, you run into all kinds of problems. First, data storage. Very deep. Second, there were problems we didn't even know could happen because nobody had ever done this before. I discovered a whole new type of problem in making a deep image that I had to overcome as part of my thesis. But of course, it's worth it because you get this cool, unfiltered look at the radio sky. And lastly, I just want to spend my last 2 minutes on questions that keep me up at night. So these are like the 5 questions that I want to answer at the end of my career. First one. Oh, yeah, bastards. I had like an amazing idea, but somebody beat me. There goes that question. Question number 2, will I prove that? Definitely not now. Question number 3, I actually just wrote a really cute paper about this. If you all want to find out, should be published in a week. Question 4 is what I want to talk about now. Question number 5, will I ever answer? No. But these are the 5 questions that I think about as my career goes on. And this database is the most interesting in addressing this 4th question. Also, I just wanted to put up these pictures of 2 tools of modern astronomy. So this picture is the Meerkat telescope array. It's the sexiest new radio interferometer in the world. Anybody know where it is? It is in South Africa. Amanda must want me to finish this talk. It's in South Africa. And it's got unprecedented looks into the universe. And lastly is computing power. Radio interferometry is a very computing intensive project. So we need new and better computers as time goes on. But the one thing I wanted to show is I'm using the data from that beautiful image that you saw to investigate this question of can large-scale magnetic fields influence the evolution of galaxies in the context of the cosmic web. So what I'm trying to do is measure these points, see how far apart they are, and try to measure this ambient magnetic field that exists throughout the entire universe. And that will be able to A, put a limit on the regulation of star formation, and B, tell us something interesting about how matter was distributed when the universe began. So they're very lofty goals, but this day, and I'm not going to succeed. Well, but this data will make a very great first look into these questions, in which future radio telescopes will be able to answer. And lastly, does anyone remember what I wanted you to get out of this talk? That's the part. What else? What? Oh, true. Yeah, that's definitely it. But it is to look up at the sky and wonder about the crazy shit that you see. So the next paper I plan on writing is, most importantly, in all of astronomy, what the hell is this thing? It looks correlated, but it's like 10 million light years across. And nobody has any idea of what the hell it is. Is that crazy? Come on, is that crazy? I think we should fund that. You guys write a letter to the NSF. In the meantime, thank you for my talk. I don't know. Oh, great. No, I don't. Oh, I can't.
Okay, so you can either raise your hand to ask a question, or you can write your question on the board here. If you don't want to ask it out loud, I'll be monitoring the board. These are all of the students for the meeting. Children have to stay for an hour.
Let's start. Your age is going to a C. Thank you. Yeah. You're still an ager. Yeah, so that's 100% true still. And what actually happens in astronomy, what ends up being interesting is we basically decide they're either particles or waves on whichever is easier. So I think in optical astronomy, and Dr. Quirk can tell me if I'm wrong, you use particles. But in radio waves, it's actually way easier to treat them as waves. So all of radio astronomy is under the assumption that they're waves. And the great thing about the fact that they can be either or is that either or gives you the right answer. It's just whichever is easier. I'd love you to tell me. So we have no idea. So it has to do something with the initial orientation of matter when the universe was created. And there's probably also some mechanisms where galaxies are shooting magnetic fields out from them. But until we can figure out how strong they are, it's hard to know what actually caused them. So that's like what I'd like to answer someday. Yeah, it's everybody's favorite one-word answer, gravity. So the gravity pulls it together. And it doesn't just happen in a blink. The things have to be close enough to where gravity can pull them together. And those only happen under very specific circumstances in the cores of those molecular clouds. But basically, things get cold enough and close enough, and gravity pulls them together. Do you want to repeat that? Or so the gravity brings them close enough to where the protons start hitting each other to make fusion. Yeah, that's a great question. So there are radio wave telescopes. So those beautiful pictures I showed of Meerkat, that's a radio wave telescope. That picture that incorrectly had the small Magellanic Cloud was the Very Large Array, which is a radio telescope in New Mexico. So they definitely exist. And everyone's new favorite sexy telescope, the James Webb Space Telescope, why doesn't it observe radio waves? Because NASA's a bummer. No, I'm just kidding. It's because you build telescopes for those different parts of the electromagnetic spectrum. And we can do amazing radio astronomy here on Earth. But infrared waves, which is what James Webb sees, can only be seen from space. So if you want to see infrareds, you got to build a fancy space telescope. Yes, redshift is ubiquitous across all the wavelengths. So when I actually measure the star formation properties of those distant galaxies, I have to take in account their redshift. Oh, it could be. Sorry. Sorry, that was just such an exciting question. It very well could be. And to me, that's what's super exciting about astronomy is maybe it is all just a coincidence, or maybe it is actually something deeper and we're seeing a new physical mechanism. And in a year or two, I hope to answer for you. What makes a galaxy a radio galaxy is a very ill-defined thing. We tend to say that it has a power above 10 to the 24 what? Watts? Yeah, 10 to the 24 watts of luminous energy. That really doesn't make a lot of sense. The better way to think about it is it's just easy to see in radio waves. That's usually when we call a galaxy a radio galaxy. No, so it was actually a zoom in about the inner quarter of that region, but it is the same regions. But we would not see light behind the moon. And as a practical problem, you really couldn't use a radio telescope looking at a place near the moon because the moon would get in the way. Love to know. What I am hedging my bet on as an astronomer is that two things. Massive galaxies are unable to get more fuel for star formation, which would be gas, and that low mass galaxies, there is some internal mechanisms within them that's not sort of like the gentleman up there's question, is not allowing the gas to get close enough for fusion to begin to happen. I think it is a mass dependent answer. No, so the observable universe is like a hard limit. It is the universe that's observable given the age of the universe. So I think, although I'm not sure, what you're alluding to is that modern telescopes are bringing us close to that edge. For example, the James Webb Space Telescope is showing us galaxies that are near the beginning of the observable universe. And radio waves similarly can be used to show us galaxies. And that's sort of what I was talking about in that picture of the star formation rate is we can look at those galaxies very close to the beginning of the universe to try to paint the picture of what happened. So it's an important part of that recipe. Yeah, so it has to do with how radio astronomy and radio interferometry has to do with large databases, and they're just a pain in the butt to deal with. So the thing that we could use most readily AI for are the fact that there's a lot of radio waves here on Earth, and they get in the way of radio waves from space. So for example, if your phone was turned off near a radio telescope, the internal electronics would still be 1 billion times stronger than any other space signal. So what we can use AI for is to get rid of those distractions, basically. And we call those flagging techniques. So that's probably the biggest next 3 to 5 year advancement due to AI. Yeah, it's definitely to show a whole greater than the sum of the parts. We can see the entire lifespan of a galaxy, but only if we look at the different wavelengths. For example, you're never going to see the beginnings of a young galaxy using radio waves. To do that, you need to look at optical or UV light. And in the same way, you're never going to see a huge black hole with millions of light years across jets if you look at just UV light. You need to look at radio waves. So the full spectrum of the electromagnetic spectrum is what allows us to make inferences about galaxies and the universe around us.